Imagine you're playing a video game where you discover a glitch that lets you walk through walls. You're not supposed to be able to do this. The game's physics engine says walls are solid, but somehow, you found a way to bypass the rules. Now imagine that glitch exists in real life. And instead of walking through walls, particles can tunnel through barriers that should be impossible to cross. This is quantum tunneling, and it's one of the weirdest, most mind-bending phenomena in physics. But here's the million-dollar question. If particles can tunnel through impossible barriers, could they also tunnel through the ultimate barrier, the speed of light itself? The ultimate speed limit. Einstein's theory of relativity tells us that nothing with mass can travel faster than light. It's not just a suggestion, it's baked into the fundamental structure of spacetime itself. As you approach light speed, you'd need infinite energy to go any faster. It's like trying to reach the top of a mountain that gets infinitely tall as you climb. But quantum mechanics has a reputation for breaking the rules we thought were unbreakable. So maybe, just maybe, there's a loophole. The ghost walk. What is quantum tunneling? To understand how quantum tunneling might hack the speed of light, we need to understand what tunneling actually is. Imagine you're a ball rolling toward a hill. In classical physics, if you don't have enough energy to roll over the hill, you bounce back. Simple. But in the quantum world, particles behave more like waves than billiard balls. And waves can do something extraordinary. They can leak through barriers they shouldn't be able to cross. Picture a ghost walking through a wall. The ghost doesn't have enough energy to break through the wall or climb over it. Instead, it simply appears on the other side, as if the wall wasn't there. That's quantum tunneling, particles behaving like quantum ghosts. This isn't science fiction. It happens billions of times per second in the device you're reading this on. The semiconductors in your phone and computer rely on electrons tunneling through barriers they classically shouldn't be able to cross. The tunnel effect, when particles bend reality. Here's where it gets really weird. When a particle tunnels through a barrier, it doesn't gradually seep through like water through a sponge. The particle's quantum wave function spreads out, exists in multiple states simultaneously, and then suddenly, pop, it appears on the other side. During this process, the particle seems to cross the barrier instantaneously. Some experiments have suggested that particles tunnel through barriers faster than light would travel the same distance. In one famous experiment, scientists fired photons at a barrier and found that the transmitted photons seemed to arrive before they should have if they traveled at light speed. Wait, doesn't this mean we've already broken the speed of light? The information paradox. Here's where things get complicated. Even if particles can tunnel faster than light, there's a catch. You can't use this to send information faster than light. And in physics, information is everything. Think of it this way. Imagine you're watching a magic show where the magician appears to teleport from one box to another. The magician seems to travel faster than humanly possible, but you can't use this trick to send a message to your friend in the audience. The teleportation is real, but it doesn't let you communicate. Quantum tunneling works similarly. The particle appears on the other side of the barrier, but you can't control when or how this happens in a way that would let you send a message. This is because of something called the no-communication theorem. Quantum mechanics allows for weird, seemingly faster-than-light phenomena, but it always prevents you from exploiting these phenomena to actually send information faster than light. The measurement problem. There's another fundamental issue. The act of measuring quantum tunneling changes the very thing you're trying to measure. It's like trying to time a ninja by shining a flashlight on them. The moment you try to observe their speed, you've already changed what they're doing. When scientists try to measure how long it takes for a particle to tunnel through a barrier, the measurement process itself interferes with the tunneling. The particle's quantum wave function collapses the moment you try to clock it. The multiverse loophole. Here's where things get really speculative. Some interpretations of quantum mechanics suggest that tunneling doesn't just let particles cross barriers. It might let them take shortcuts through spacetime itself. In certain theories of quantum gravity, spacetime isn't smooth like a sheet of paper. At the smallest scales, it's more like a foamy sea of virtual particles and fluctuating dimensions. Some physicists speculate that particles might tunnel through these quantum foam wormholes, taking shortcuts through higher dimensions. Think of it like GPS navigation. If you're driving from point A to point B, GPS might route you through side streets that are technically longer but actually faster due to traffic conditions. Maybe particles can access quantum side streets that we haven't discovered yet. The engineering challenge. Even if we could somehow use quantum tunneling to send information faster than light, we'd face enormous engineering challenges. Quantum effects are incredibly fragile. They work at the scale of individual atoms and particles, but they tend to disappear when you try to scale them up. It's like trying to build a bridge out of soap bubbles. Each individual bubble is beautiful and follows its own physics, but the moment you try to connect them into something larger, they pop. This is called decoherence, and it's the reason we don't see quantum effects in our everyday world. The causality paradox. But let's say we somehow solved all these problems. If you can send information faster than light, then according to relativity, you can send information backward in time. This leads to paradoxes like the grandfather paradox. You could theoretically send yourself a message preventing you from sending the message in the first place. The universe seems to have built-in safeguards against these paradoxes. Every time physicists think they found a way to violate causality, they discover new physics that prevents it. The horizon of possibility. So can we hack the speed of light with quantum tunneling? The honest answer is, probably not in the way you'd want to. Quantum tunneling is real, and it does seem to allow particles to cross barriers in ways that appear to violate classical physics. But every time we try to exploit this to send information faster than light, we run into fundamental barriers: the no-communication theorem, the measurement problem, decoherence, and causality paradoxes. But here's the thing about fundamental barriers in physics: they're not always as fundamental as they seem. Quantum mechanics itself was discovered because physicists found phenomena that violated classical physics. Maybe the speed of light isn't the ultimate limit we think it is. The question that keeps physicists awake. The deeper question isn't whether we can hack the speed of light, it's whether the speed of light is actually the speed limit we think it is. Recent discoveries in quantum mechanics suggest that reality might be far stranger and more flexible than we imagined. Maybe particles aren't just tunneling through barriers in our universe. Maybe they're tunneling between universes. Maybe the speed of light is just the speed limit for information traveling through normal spacetime, but quantum information might have access to express lanes we haven't discovered yet. The universe has surprised us before. Quantum mechanics was considered impossible until it wasn't. Black holes were thought to be purely theoretical until we photographed one. Maybe faster-than-light communication is just the next impossible thing waiting to become possible. What if the speed of light isn't the ultimate cosmic speed limit, but just the speed limit for classical information? What if quantum information plays by different rules entirely? Ready to dive deeper into cosmic mysteries? Don't miss our next exploration into how quantum entanglement might be creating hidden connections across the universe, where we'll discover what Einstein called spooky action at a distance, and why it might hold the key to understanding reality itself.